Here we're going to gain a little more practice solving inequalities. And let's do an example. We're asked to solve and graph the solution set and write it in interval notation. Now first of all, that word graph, right? That doesn't mean graph on an xy coordinate system. You only do that when you have two variables. I can see on this problem I only have one variable, right? So that means this graph here implies that we want to graph the solution set on a number line. Okay, so the first thing I'm going to do, because this involves a fraction, is I'm going to clear fractions. And I'm going to do that by multiplying both sides by -3. So parentheses are on the left-hand side, -3, and a set of parentheses are on the right-hand side as well. And let's see, the -3's cancel, right? That's why we did it. And on the left-hand side, we just have 5 minus d. And now, do you see how you multiplied both sides by a negative? That means you have to switch the direction of the inequality. So rather than greater than or equal to, it becomes less than or equal to. And now -2 times -3 is +6. So now we want to isolate the d, so we're going to first subtract 5 from both sides. And let's see, that leaves us with -d is less than or equal to +1. Now, I don't switch the inequality here because, well, you never switch when you subtract something from both sides. It's only multiplying or dividing something by a negative. Okay, at this stage, the d is not yet quite by itself. Now, that -d I can regard as -1 times d. So now I'm going to divide both sides by -1 to get rid of this factor of -1 right there. So let's see, -1d divided by -1 is just d, that's why we did it, is greater than or equal to 1 divided by -1, which is -1. Okay, so now we want to graph the set of numbers that makes this true, and we want to do that on a number line. So let's draw our number line here. And we know it's a number line because there's only one variable. And on the number line, let's locate -1. So if this is like -2, and then -1 and 0. Let's see, we want all the numbers, well, we want numbers here that are greater than or equal to -1, and that means greater than -1, right, to the right of -1. Now, because it's greater than or equal to, right, the little or equal to symbol there, that's why we need a bracket on the -1, indicating that the number -1 itself is included. So I put a bracket on the -1, and I shade to the right like so. So that's the graph of the solution set, and then writing that solution set in interval notation, that's going to be -1 all the way to infinity. Okay, so this would be my complete answer. Just one word about this problem. At this stage, when we had -d was less than or equal to 1, right, I divided both sides by -1. Sometimes people accidentally add 1 here, and you don't want to add 1, and the reason is because this is the same as -1 times d, right? This is multiplication right here, and to undo multiplication, we need to use division like we did here. Okay, let's try another one like that. Okay, we're going to solve this fairly complicated inequality, and it's complicated, but there's only one variable, right? So notice that I didn't write the instructions out here, but when I write solve, it's going to be, we're going to assume that we're still going to represent the solution set by graphing it and also by using interval notation. Okay, so, and there's only one variable, so I'm going to be graphing on a number line just like before. And I notice that I have fractions again. So I'm going to clear fractions once again, and so I need to find the LCD of 2, 5, and 6. Well, what's the smallest number that 2, 5, and 6 all go into? Let's see, that's going to be 30, right? So you could find that formally, or you can just see it. So multiply both sides by that LCD, which is 30. Let's write it as 30 over 1, and then parentheses on the right-hand side as well. Okay, now it's subtraction here, right? And that means this 30 has to be distributed. So it gets multiplied by this first, and then it's going to get multiplied by all of this. And on the right-hand side, it's not distribution because there's only a single term right there. Okay, let's see. Now, when you multiply these two together, 2 goes into 30, it's going to go 15 times, right? Now, that 15 that you get, you have to multiply that by the numerator x minus 3. Let's save that for the next step. So I'm putting parentheses here because this is subtraction, which means this 15 has to be distributed in the next step. Okay, then minus, well, let's see, 5 goes into 30. That's going to go 6 times, right? And now I'm going to put parentheses around that x minus 2, right? Around this numerator, because this negative 6 is going to be distributed. How did I know to do that? You always use parentheses when the numerator is either addition or subtraction. In both these cases, subtraction, indicating that I'm going to need distribution in the next step. Okay, then less than or equal to, let's see, a negative times a positive is a negative, and 6 goes into 35 times, so it'll be negative 5x, and the fractions have been cleared. Now we're going to distribute the 15 and also distribute the negative 6, so it's going to be 15x minus 45 minus 6x, right? Negative 6 times x is negative 6x, and negative 6 times negative 2 is positive 12, and that's going to be less than or equal to negative 5x. And now combining like terms on the right, 15x minus 6x is 9x. Let's try that again. It's 9x. And then negative 45 plus 12, that's going to be negative 33. And that's less than or equal to negative 5x. Okay, now we're trying to get x on one side, right? So let's get x on the left. So I'm going to add 5x to both sides. And then we're looking at, let's see, it's going to be 9x plus 5x is 14x minus 33 is less than or equal to 0 on the right-hand side. So we're going to add 33 to both sides now. So now we're looking at 14x is less than or equal to 33. Finally, let's divide both sides by 14. And so let's write what we've got up here now. We've got x is, let's see, less than or equal to 33 over 14. Okay, now let's convert that to a mixed number, because the first thing we're going to do is we're going to graph this on a number line, right? Now, usually we leave our answers as improper fractions, but the exceptions to that are when you are plotting, or when you're graphing, or when you have an application. So in this case, we're going to be plotting the point 33 over 14. In that case, convert it to a mixed number. So let's say the way we do that is we take the denominator 14 and divide it into that numerator 33, and it goes in twice, and we have 28. Subtract that off, and we've got 5. So 33 over 14, that's the same thing as 2 and 5/14. So x is less than or equal to that. So let's go ahead and locate that on a number line now. So when I look at 2 and 5/14, I say, it's bigger than 2, but not quite 3. So if this is 0, 1, 2, and 3, right? Now you can make an approximation here, and my approximation is as follows. 5 over 14 is a little less than 7 over 14, right? 7 over 14 is the same as a half. So 7 over 14, if I had 2 and 7/14, that'd be 2.5. This is a little less than that, right? So if 2.5 is maybe right here, the number we want is a little bit less than that, so maybe right there. Maybe that's 2 and 5/14. And we want numbers that are less than or equal to that, right? So that means we want a bracket because it's less than or equal to, and the bracket opens this way because we want numbers less than that. So we shade like that. So this is a graphical representation of the solution set. And then as far as an interval is concerned, well, we want all the numbers less than that, right? So that's going to be negative infinity, and then the largest number in that set is going to be, now here you can write 2 and 5/14, but people often do this. They just write 33 over 14. Either way is okay, but we're going to need a bracket on that. So this will be our answer. Okay, so right here you could either write 33/14 like I did, or you can write 2 and 5/14. Either answer would be acceptable. Okay, let's try one more. Let's solve 1/2 times x minus 5 is greater than 1/2 x plus 6. So the first thing I'm going to do is distribute the 1/2. Now I do want to clear fractions, but we usually do multiplication first before clearing fractions. So it's going to be 1/2 x minus 5/2 is greater than 1/2 x plus 6. And so let's clear fractions, multiply both sides by 2. Let's write that as 2 over 1. And because it's subtraction right here, I have to distribute that 2. So when I first distribute here, the 2's cancel, and I have just x. And then when I multiply 2 over 1 by 5/2, the 2's cancel there. And I have just 5. So it's x minus 5 is greater than, now it's addition here, so we have to distribute the 2, right? Like so. So 2 times 1/2 is 1, but I still have the x. So it's x plus 12. And now we're trying to get x on one side, so let's subtract x from both sides. Whenever you have x on both sides, you always want to subtract off x or get rid of that term containing x on one side. Right? Try to just get x on one side. So my thought process was, hey, let's get rid of that x there. And I did that by subtracting x from both sides. Now it turns out the x's cancel here as well, right? Because x minus x is 0. And I'm left with negative 5 is greater than, well, x minus x is 0 again, and I have positive 12. Now, notice that this is an inequality with no variable in it, right? There's no longer an x. What that means is when you have statements, equations, or inequalities, the statement always falls into one of 3 camps. The statement is either true, or the statement is false, right? Or the statement is what we call conditionally true. Okay, now, if I write down a few statements here, if I write this, 7 is greater than 3, well, that's clearly true, right? And if I say, 5 is greater than 1, that's true as well. And then finally, if you say, 2 is less than negative 1, that's clearly false. So these are examples of statements that are either true or false. Now, conditionally true, those are statements that can be made true with the correct substitution. So for example, if I write this, x is greater than 7, well, that statement is true if you replace an x with like an 8 or 7.5 or anything larger than 7, right? So this statement right here is what we call conditionally true. So an example of a conditionally true statement would be in the previous problem. Let me go back to that previous problem for a minute. So this is an example right here of a conditionally true statement. If you can plug in a number here that's less than or equal to 33 over 14, then the statement is true. Like for example, 33 over 14 is the same as 2 and 5/14. So if I plug in 1, that statement is true because 1 is less than that. Okay? So most of the problems actually we see in math are situations where the statements are conditionally true. Let's go back to our problem now, our last problem. So this, right, this is conditionally true, these are true, and this is false. So let me ask you, is this statement true, false, or conditionally true? Well, it's false, right? Negative 5 is not greater than 12. So this statement right here is flat out false. Now, what does that mean? The first statement, right, the first inequality, the second inequality, and then the third inequality, these are all in math what we call logically equivalent. Now what that means is that they're true and false under exactly the same conditions, okay? That's the logic of what we're doing in algebra, is we are creating statements that are logically equivalent. Now what that means is that when we say that in math, logically equivalent, that means they have the same solution set. And that means they are true and false under the same conditions, okay? So this statement is false. Now, false means never true. Okay, it's just a plain old false statement. That means this must be false. Why? Because these are logically equivalent, right? They're true and false under the same condition. So if this is false, never true, and that means the original problem is false, never true. Now, never true means that you can't find a value of x to plug it in there such that the statement is true. Never true is the same thing as saying that there's no solution. Okay, so that's our answer to this problem. There's no solution because we can't possibly make it true because it's always false, and I know it's always false because it's logically equivalent to this statement, which is logically false, or which is always false. Okay, that's a little subtle, but that helps us with some of the theory that we're using with solving not only inequalities but equations as well. Okay, until next time.